Depth from defocus on a transmissive diffraction mask-based sensor. Here I will briefly discuss the classical depth from defocus problem. On the left, we show our input image. The plane of focus for this scene is between the U and M blocks. We can use Zhuo and Sim's method to estimate the defocus blur here. However, under a symmetric aperture, the defocus estimates from a single image have an inherent front-back ambiguity. That is, there are two depth planes, one behind the plane of focus and another in front of it, that will produce the same defocused blur. This is because the blurring kernel is symmetric. In this work, we will demonstrate how this front-back ambiguity in defocus estimates can be resolved using a novel transmissive diffraction mask-based sensor, or a TDM-based sensor. The TDM-based sensor consists of a phase-modulated diffraction mask that sits on top of an off-the-shelf CMOS sensor. As this is a transmissive mask, the TDM-based sensor has a high quantum efficiency. The TDM works with existing pixel architectures and there is no need for custom pixels. For our work, we use a TDM with vertically oriented gratings that have a period of 2 pixels. The vertical gratings introduce an asymmetry in the response of a system along the x-axis. The TDM produces two characteristic responses, the sum response and the diff response. Each TDM pixel pair produces one sum and one diff response. The sum response is obtained by adding the responses of the two pixels under a single period of the PDM, while the diff response is their difference. The sum response is symmetric, and hence the sum image is very similar to the intensity image from conventional 2D image sensors. The diff response, on the other hand, is asymmetric. The diff is a sign response, and so the positive values are shown in red here and the negative in blue. In the paper, we provide a more detailed model of the diff and sum responses. Next, we will demonstrate a key property of the sum and diff responses with an experiment. For this experiment, we image a Gaussian whose width spans a single pixel on a monitor. The distance between the monitor and the sensor is increased in 4 steps, d0 through d3. The distances were chosen such that the focus distance, defocus, of the system was between d1 and d2. Further, we also scaled the Gaussian with distance such that its visual angle with respect to the camera remained constant. The first row shows the sum images. Observe that the blur decreases from d0 to d1 as we move towards the plane of focus. And once we've crossed it and move further away from it, in d2 to d3, the blur increases again. Between pre and post focus, the blur kernel gets flipped left, right, up, down. For the sum image, this flip is not detected, since the sum kernel is symmetric, leading to a twofold ambiguity. However, this flip can be easily observed in the diff images since it has an asymmetric blur kernel. We show the diff images in the second row. Observe the two hemispheres in the diff images. For the pre-focus distances, the left hemisphere has a negative response and the right a positive one, while for the post-focus distances, the negative response is to the right and the positive to the left. Thus, as we move from pre-focus to post-focus, the two hemispheres of the diff response flip sign as a result of the flip in the diff kernel. To demonstrate our method, let us walk through an example. The scene here consists of a few letter blocks. The U block is in the post-focus region and the M block is in pre-focus. Here, we see the sum image computed from the sensor. This is the same image as from slide 1 of the talk. We apply the classical DFT method on this image. And here is the diff image. Recall that the diff is a signed response. So here, the positive values are shown in red and the negative in blue. Also, observe that only the vertical and diagonal edges induce a strong diff response and that the horizontal edges are missing. This is because the vertically oriented diffraction grating can only diffract light incident along that direction. Next, let us look at the gradient of the sum response along the x-axis. Throughout this presentation, we refer to this x gradient simply as the gradient image. You might observe that the gradient image looks very similar to the diff image, but as we will see in the next slide, there is a very key difference. In the diff and gradient images on the left, there is a slice through the U's and another one through the M's. On the right, we show the corresponding line plots. The plot on the left is through the U's, while the one on the right is through the M's. The peaks in these plots correspond to the edges. For the U block, The diff and the gradient images share the same sign. That is, when the gradient is positive, so is the diff, and vice versa. While on the M block, they have the opposite signs. So when the gradient is positive, the diff is negative, while when the gradient is negative, the diff is positive. This characteristic of the TDM responses is because while the sum is a symmetric response, the diff is an asymmetric one. Thus, while the profile of the sum kernel is unaltered as we move from pre-focus to post, the diff kernel, which has a left-right asymmetry, gets flipped. The sign information of the diff and the gradient images is crucial for us to tell if the edge is in pre-focus or in post-focus. We're going to use this sign information in our method on the next slide. We can use this relationship between the signs of the diff and the gradient to define a pre-post edge map, which can tell us if the edges are behind the plane of focus or in front of it. In the pre-post edge map, we define an edge to have diff and gradient responses sufficiently larger than a chosen threshold. P is equal to sine of diff times the sine of the gradient. So P is +1 when both the diff and the gradient at a given pixel have the same sign. That is, both are positive or both are negative. P is -1 when the diff and the gradient have the opposite signs. Note that, again, since our mask only has vertical gradings, this sensor cannot provide pre-post estimates for non-horizontal edges. As we mentioned towards the start of the presentation, we use Jiho and Sim's method to estimate our defocus values for the non-horizontal edges. These ambiguous defocus estimates are then combined with our pre-post edge map from the previous slide to obtain defocus estimates that are free from any two-fold ambiguity. We can resolve the ambiguous estimates from the earlier slide by multiplying them with the pre-post edge map. Recall that in the pre-post edge map, a value of +1 corresponds to a post-focus edge and -1 to a pre-focus edge. In the resolved defocus map, positive defocus values are from post-focus edges and negative ones from pre-focus edges. Here, we show the unambiguous defocus estimates obtained using this approach. We have some more interesting scenes in the next few slides. This scene is a stack of books at decreasing distances from left to right. The scene has mostly vertical edges. In the pre-post edge map to the right, we can see that the edges to the left are in post-focus region and those to the right in pre-focus. Further, the focus is around here. On the left is a signed sparse defocus map from a method which combines the pre-post edge estimates with the unsigned defocus estimates from Jiho and Sim's method. We can see from the map that the defocus estimates are decreasing from left to right, implying increasing depth. We apply a very simple strategy to these sparse results to produce the dense map on the right. This next scene has more edge orientations. Balls of crumpled paper are placed on a checkerboard floor. Far in the background is a flat wall with various black and white edges. Again, the pre-post edge estimates are shown to the right of the sum image. Note that the horizontal edges of the checkerboard and the back wall are missing since our TDM only has vertical gradings. To the left, we can see the defocus estimates for the paper balls with the corresponding dense estimates to its right. The defocus estimates increase from bottom to top in trend with the depth. Our final scene consists of various figurines on a toy train. The focus is roughly in the middle of the second card. The animal figurines contain more complex edge orientation, and our method is able to produce a pre-post edge map for all edges that have a non-zero vertical component. And here are the final sparse and dense defocus maps. Note that the defocus estimates for the train and the figurines are increasing from right to left, again in trend with the depth. In this work, we show how a TDM can change the response of a system from symmetric to asymmetric. We show how we can decouple the asymmetric response introduced by the TDM and the symmetric response of the system as the diff and sum responses respectively. Traditional DFT methods can then be applied to the sum image to produce defocus estimates with a twofold front-back ambiguity, which can then be resolved using the asymmetric diff response.